Okay, this is the Chapter 5 online quiz. Which of these best describes why some materials are permanent magnets, so-called ferromagnetic? Not because they have charges, all of them have charges, not because they're made of metal, because not all metals are permanent magnets, and not because they're found in the center of the Earth, but because the magnetic domains of are all aligned in the same direction. Which of the best explains why a permanent magnet is magnetized? Oh my gosh, this is basically the same question, but the answer here is the magnetic domains are magnetized. Not because it has a current through it, in fact it doesn't have a current through it. Electrons do produce their own magnetic field, but that's true of all electrons, not just in permanent magnets. And ferromagnetic materials are not always magnetic, right? They're just able to be magnetized. Which pole of a magnet points towards the magnetic north pole? That would be the south pole. So if you imagine the Earth here, this is the northern geographic pole, this is the southern geographic pole. However, if we draw a bar magnet on the Earth, this is the northern magnetic pole and the southern geographic pole. And then if I have a compass over here, here's my magnet on my compass, the northern pole of this magnet points to the north pole, and the southern pole points to the south pole, but the southern pole also points to the northern magnetic pole. So A is the right answer. A negative charge enters a magnetic field as shown. In what direction will it feel a force? Okay, you do your right-hand rule, fingers in the direction of V. Your palm goes in the direction of the magnetic field. So the magnetic field is out of the page. So you would find that the force is to the right. But because it's a negative particle, you take the opposite of that, so the force is to the left. Push piece of copper wire through a magnetic field as shown in this figure. All right, I did this before, but I'm going to say instead I have this velocity. So I have these charges. Let's make this bigger. I have these positive charges inside the wire with a certain velocity going through this magnetic field. So I let my fingers go in the direction of V. They fold towards the magnetic field, and that gives a force on those charges in this direction, right, which causes a current to move up in the wire. You push a 1 meter long piece of copper wire through a magnetic field, as shown, push with a force of 12 newtons. All right, so we say F equals ILB sine of theta. Here, theta is 90 degrees, so that just goes to 1. So 12 newtons equals IL is 1 meter. And the magnetic field is 2.4 Tesla. So I is 12 over 2.4, which is equal to 5 amps. All right, this shows a loop of wire. In what direction does the loop initially turn? So I'll just take one. First of all, the magnetic field moves from this direction. So imagine this current over here. I have a current that is into the page and a magnetic field that is to the right. So I use my right-hand rule. This is just the right-hand side. On the left-hand side, I would have a current out of the page and a magnetic field here. So taking this side, current is into the page, magnetic field, so that gives me a force that is down. Over here, you would find a force that is up. So I have an upward force on this side and a downward force on this side. That causes rotation in the clockwise direction. So clockwise. All right, charged particle enters a mass spectrometer. The details, what is a particle? All right, we start with our R equals mv over qb. And I want to solve for the mass to charge ratio. So that's going to be RB over V. And let's see here. So my radius is 0.052. B is 0.4. And our velocity is 2 million meters per second. I get 1.04 times 10 to the minus 8. This is going to be kilograms per coulomb. And then I'd go through and I'd find which of these has a mass to charge ratio of 1.04 times 10 to the minus 8. And it looks like the only one of these would actually give me 1.04 would be dividing these two numbers. So it has to be hydrogen is the unknown particle. What is the direction of the magnetic field? Well, let's take this wire first. It has a current in this direction. So that means that on this side, the magnetic field is into the page. On this side, it's out of the page. Then due to this wire, the magnetic field is, or the current is up. So on this side, it's into the page, and over here, it's out of the page. So at point A, it's out of the page. This figure shows 3 configurations of 4 wires, either coming or going. Which has the largest magnetic field? All right, so let's take this wire first. It's coming out of the page, and so the magnetic field is going in this direction. And so at point P, my magnetic field looks like that. Due to this one, it's going in this direction. And so at point P, it looks like that. Due to this one, it's going in this direction. So at point P, it looks like that. And then due to, let's see, on this wire, it goes in that direction. They all go counterclockwise, but they all give a vector here that's in a different direction. So this is a net magnetic field equal to 0 because they all cancel out. Now let's look at this one. Due to this one, it's into the page, and so the magnetic field is in that direction. Similarly here, in that direction, here, in that direction, and there in that direction. Now, due to this one, it looks like that. Let me put some color on here. So we'll take this one, looks like that. Due to this one right here, it's going to be in this direction. Notice here, I have a tangent circle, goes around like that, and so at this point, my vector comes off tangent to that circle. All right, looking at this one, it's going to be in this direction. What haven't I used? Which one haven't I done? Oh, this one right here. It's going to be in this direction. All right, so this gives a net force in this direction, or a net magnetic field. B is going to be the right answer. Let's go ahead and do C, though. Due to this one, which is out of the page, the magnetic field looks like this. Similarly, due to this one, magnetic field looks like that. It's going to be the opposite for these others. The magnetic fields, excuse me, I'm sorry. This one's going to be in this direction, all right? Counterclockwise here, clockwise here, and clockwise here, all right? And then if I look at the vectors, due to this red, it's going to be up and like that. For this one right here, it's going to be in that direction. For the blue, in that direction, and then the green be in that direction. So the net magnetic field here is 0. All right, you know, positive charge enters the uniform magnetic field. What is the direction of the magnetic force? All right, fingers in the direction of V. Fingers in the direction of V, they fold towards B. The magnetic force is to the left for a positive charge. Here we go, I have another one. VB, magnetic force is up. Here I have V is up, magnetic field is to the right. So the magnetic force is into the page. Here, the angle theta equals 0 degrees, and the sine of 0 degrees equals 0. Remember, F equals QVB sine of theta, and in this case, that force is equal to 0. All right, here, a beam of atoms enters magnetic field. These are atoms, so Q is equal to 0, so the force is equal to 0, so this second option. Proton beam enters magnetic field. What is the direction of the magnetic field? B. All right, so my velocity is initially in this direction, and my force is in this direction. I want to know what magnetic field generates that force. All right, that is going to be a magnetic field into the page. Notice, by the way, up here that now my velocity is here, but with that magnetic field, my force is now in that direction. And so this force is a centripetal force, which comes up when we're talking about the spectrometer, the mass spectrometer equation. All right, here, the cyclotron equation, excuse me, R equals mv over qb. Here I want to know which particle has the bigger charge. So if Q is big, that means that R is going to be small. They have the same speed and the same mass, and the magnetic field is all the same. So the one with the bigger charge is going to be the one with the smaller radius. That would be B. What happens to the kinetic energy of the proton? Remember, the magnetic force is a centripetal force. If you remember something about centripetal forces, like a ball on a string, for example, that is a centripetal force that causes that string that ball to go into a circular path. All right, I have a centripetal force. It does not change the magnitude of the velocity, and the same is true for magnetic forces. They do not change the magnitude of the velocity. So here, the answer is C. The kinetic energy of the proton will remain the same. All right, here I have a beam of electrons. They're going through an electric field. This is used, by the way, where you have modulating electric and magnetic fields to change the direction of beams of electrons or protons quite a bit. So here I have an electric field. This electric field acting on this beam of electrons would generate a force that would be downward. All right, the electric field has a force on the electrons that is opposite the direction of the field lines. That's based on our definition of electric field lines. Electric field lines, positive charges feel a force in the same direction as the field lines. So, in order for this beam of electrons to go undeflected, there has to be another force, FB, that runs opposed, equal but opposite to the electric force. So, I know I have a velocity in this direction, and a force, my magnetic force in this direction. So what is the magnetic field that generates this? That has to be into the page. So my magnetic field will be into the page, and the electric field is up as it's drawn. Horizontal wire carries a current, and vertical magnetic field was the direction of the force on the wire. All right, this is our second application of the right-hand rule. Fingers in the direction of I. Your palm in the direction of B, and your thumb comes out of the page. So E is the right answer. The force is out of the page. Here, the current and magnetic field are in the same direction. So theta equals 0 degrees, so there is 0 force acting on it. Here I have a rectangular current loop. What is the direction of the net force on the loop? All right, well, the net force is going to be 0 because I have one current in this direction, and one current in this direction, current in this direction, and a current in this direction. So whatever the force is on this one, you're going to have the opposite force on this one. And the same is true for the other two sides. But what if I have this? This is very similar. This might be identical to the other question. Here I have a magnetic field that runs in this direction, and I have a current that goes in this direction. So I have a current that is into the page, and a magnetic field that is to the right. And I can find the direction of my force. It's going to be down. So the force due to these two is going to be down. So I have a downward force here. And then you can do the same thing on the left side, and you'll find that the force is up. So that would be a clockwise rotation. Okay, this is shows two wires. What is the direction of the magnetic field? All right, let's first consider this wire. It's into the page, and so the magnetic field goes around in this direction. So at the point P, the magnetic field will be in that direction. Now, you can imagine this wire right here, the watt current is out of the page, and so the magnetic field will go around in this direction, causing a magnetic field at point P in that direction, which is tangent to the circle, and then I just translated up here. Now the net of these is going to be in that direction. That is direction C. Okay, this is very similar to the previous one. Each of these wires carries the same current, either into or out of the page. Let's go through. Let's start here. This one is into the page, and so it causes a clockwise current. Likewise, you'll have a clockwise current here. Here you're going to have a counterclockwise. This is from the curl rule. Counterclockwise. Now let's draw our vectors at this point. Due to this one, it's going to be in that direction. Due to this one, it's going to be in that direction. Due to this one, it'll look like that. And then let's see, due to this one, it's going to be in that direction. All right, so the magnetic field for this first one is 0, so that's not it likely. Now let's look at these other two. By my curl rule, right? And then at this point right here, I'll have one in that direction. All right, so the net magnetic field will be in that direction. Looks like that's going to be our winner, but let's do this other one. All right, so these are all going to be in this direction. They're all counterclockwise by the curl rule. See, am I missing a color here? There we go. All right, so right there, right there. All right, so they look like that. So this one has a magnetic field equal to 0. This was our answer. All right, a positive charge moves parallel to a wire. If current is suddenly turned on, what direction will the force act? Okay, well, first of all, what is the direction of the magnetic field produced by this wire? Let our thumb go in the direction of I. On this side, it will be into the page. On this side, out of the page. So then I have a velocity vector here and a magnetic field that's out of the page. What is the direction of the force? It's going to be to the right. So my force is to the right. That's in the positive x direction. I have two wires here. Anytime you have two wires with currents going in the same direction, they're going to feel a force that is attracted to one another. I can imagine this. I have this wire right here. It generates a magnetic field that is into the page, out of the page like this. So that's my magnetic field. And then I imagine, well, this has a current flowing through it, I. And so I, given this magnetic field, will give you a force that is attractive towards that other one. And then in a similar way, you're going to have another force that's in that direction. So currents in the same direction will be attractive. What is the direction of the magnetic field at the center of the point P? All right, this is like in a solenoid switch or a current loop. You can use your curl rule, let your fingers go in the direction of I here. The magnetic field is into the page here and out of the page here. All right, so the answer is going to be E, out of the page, and you can actually go around all sides of the loop, and you'll find that in the middle, at least with this current configuration, is going to be out of the page. And that's all.